Hello guys, welcome to the lecture series of Signals and Systems. This is lecture 1 and in this video we will review whatever happened in the introductory slides and then we'll see what is the transformation of the independent variable, including the properties of shifting, scaling and reversal, and then finally we'll go ahead and classify the signals. So let's get started. So to start with, we'll again define what is a signal. So what is a signal? A signal is a set of data or information. A signal is a set of data or information which may describe a wide variety of physical phenomena. Which may describe a wide variety of physical phenomena, right? So basically you can just consider it as some information conveyed through some variation in the physical phenomena, right? And as example, you can take your television signals or the telephone signals, even the mobile phones, right? And at the basic level, you can consider voltage, current, and charge, etc. Right? Okay. So next we define what is a system. So what is a system? So a system is an interconnect of components, devices, and subsystems. And usually what happens? So it can be viewed as a process in which the input signal is transformed or additional information is extracted, right? So again, to give examples to this, you can just see the corresponding. For TV signals, if you have the set-top box, right? Set-top box. So it transforms the incoming TV signals so that you can watch it on the TV. And for telephone signals, you have the telephone itself. So it is also a system. And for voltage, current, charge, you can call circuits or networks as a system with some inputs and outputs, okay, and etc. And we also discuss how to mathematically represent these, right? So signal, it's a function of one or more independent variables, and system, it is the function of the signal itself, okay? So next, what did we see? Next we saw about the size of a signal. So what did we define the size of the signal to be? It is a measure of the strength or largeness of a signal. And what did we also see? We saw like only amplitude or the width time period alone cannot decide the strength or the largeness of the signal. So we require both, right? So both the amplitude and the duration of the signal matters. So then we went ahead and defined two quantities. So one is the energy of the signal, or the signal energy of the signal. So what did we define the energy of the signal as? It is nothing but the area under the x square of t, right? So from minus infinity to infinity, if x of t is real, otherwise what did we do? We just took the modular square for complex quantities. So if x of t is complex, so it is only sufficient to say, write only this, because this holds for both real and complex. So we'll just only use this. So we can take this to be the energy of the signal. And then what did we define for signals who were having like infinite energy but still can differ in some aspects? So for them, we define what is called as the power of the signal. So what we define the power as? So it is the time average of the energy. So we defined it in terms of limits, right? So we consider some interval minus t by 2 to t by 2, and we take the energy of that, and then we average it and we tend the limits to infinity. So let us go ahead and see some examples of these formulas, right? So example. So what do we have? Let's consider a signal x of t. x1 of t, and let's say its amplitude is 3, and it is like a rectangular signal, and it lasts for, let's say, t equal to 2, from 0 to 2. So now you can see it has a finite duration and finite amplitude, right? So you can easily calculate the energy. So we have the formula here, correct? So what is Ex1? Ex1 is minus infinity to infinity x of t mod whole square dt. But for t less than 0 and t greater than 2, it is 0. X of t is 0. So we'll have from 0 to 2, and x of t is 3. So 3 square dt, which is nothing but integral 0 to 2, 9 dt. And 9 you can take out and integrate from 0 to 2. So what will you get? X from 0 to 2, which is nothing but 9 into 2 minus 0, which is 2. So we'll get 18. So what will be the units? Let's say x1 of t is in volt and t is in seconds. Then what will be the units? It will be whole square into seconds. So this is the energy. Similarly, let's now try to calculate the power for another example. I'll take another signal. Example 2. So now let us consider x2 of t as some sinusoid. Okay, C sine omega naught t. And omega naught is nothing but 2 pi by t naught. So t naught is the time period. Okay. So how will this look on a graph? So you have the time axis and x2 of t. So you have the sine. So it is something like this on both sides. And this will be c and minus c. and these will be the time intervals, right? The period t naught, and this side it will be minus t naught, and so on. And as you can see, it extends from minus infinity to infinity. So if you try to calculate the energy Ex2, so what do? You need to find x square of t first. So x square of t, what will happen to that? Let's say this one. So you will get same, but it will all be positive, right? So the amplitude will be c square max. But you can see it's all positive. And again, this is also like from minus infinity to infinity. Extends from minus infinity to infinity. So what is Ex2 then? So it is minus infinity to infinity mod x2 of t square dt. Do you think it will have a finite value? No, right? Because if you consider only this interval, let's say it has some finite value a, then you have infinite copies of these, right? So you will get answer as some a into infinity, so which will be infinity. So E of Ex2 is not finite. So then we can go ahead and try to calculate the power. So power, what is the formula? You have it here, right? So it is limit t tends to infinity 1 by t integral minus t by 2 to t by 2 mod x of t whole square dt. It is just the average of energy. So what do we do in that case? So it is average, time average of energy. So we calculate energy over one time period and divided by the time period. Agreed? So this is nothing different from the formula given here, right? So if I can just replace it by t naught and it will be the same. Okay. So what is energy over one time period? It will be minus t naught by 2 to t naught by 2 and x2 of t whole square dt divided by t naught itself. And what is x2 of t? So x2 of t is here, c sine omega naught t. So 1 by t naught integral minus t naught by 2 to t naught by 2 c square sine square omega naught t dt. So c square we can take it out. C square by t naught integral minus t naught by 2 to t naught by 2 sine square omega naught t. So integrating sine square is not difficult for us, right? So we have cos 2x is nothing but 1 minus 2 sine square x. So sine square x will be 1 minus cos 2x by 2, right? So then what will we have here? C square by t naught integral minus t naught by 2 to t naught by 2 1 minus cos 2 omega naught t by 2 into dt. So now we can take the 2 common out. So we have two terms, minus t naught by 2 to t naught by 2 1 dt plus or minus integral minus t naught by 2 to t naught by 2 cos 2 omega naught t dt, right? So what is the period of this cos 2 omega naught t? So it is 2 omega naught is equal to 2 pi by t naught prime, which implies that t naught prime is pi by omega naught. Or in other words, t naught prime is nothing but 2 t naught, right? It is twice the time period. It is t naught by 2, which is half the time period, right? So, but if you see, what is this integral saying? It is the average of cos to omega naught t over 2 time periods of t naught prime, right? But cos omega naught t, if any cos if you take over one period itself, okay, this is, I'll draw it as a cos, right? So if you see over one period itself, its average will be 0, right? So if you take over any number of periods, integer number of periods, it will be 0. So this term will go to 0. So we are only left with the first term. So this is simple. So integral of 1 dt will give you t itself, and from t naught by minus t naught by 2 to t naught by 2 will just be addition of the limits. So it will give you t naught. So this is c square by 2 t naught into t naught. So t naught cancels. So we'll get half c square. So we found the power of a simple sinusoidal signal with amplitude c. And what it is? It is half into the amplitude square, right? Okay. So now we can go ahead and see the transformation of independent variables. Transformation of independent variables. Variable. So in this case, we are mostly dealing with one variable, right? And that one variable, we are for convenience referring to it as time, but it needn't be the case. But anyway, we'll see what is called as the time shifting and time scaling and time reversal. Right? So the independent variable here is time. So the transformation is the shifting, scaling and the reversal operation. So first we'll see the time shifting. So let us consider a signal x of t. So I'll represent it graphically. So let it be some rectangular. Okay. So, and then with respect to t, and then I shift it to the right. So shift x of t to right by t seconds. This is also nothing but delaying, right? Delaying. So they are equivalent. So how will now this look like? How will x of t look like? So let's say this is the previous one. So now it will be moved here. Right, and this distance or this time will be t seconds. So let me call it this as the second signal, some phi of t. Okay. And if you see, the amplitude will remain same. Let's, if I take one here. So amplitude remains same. Amplitude remains same. So only the signal has shifted in time. Correct? Hence it is called as time shifting. So now what happens? So phi of t. So whatever happens in x of t happens at t plus capital T, right? So whatever happens at t1 let's say, for x of t happens at t1 plus t for phi of t. Agreed? Right? So then what can we write? Phi of t1 plus t is nothing but x of t. X of t1, correct? So this wording and this equation are synonymous, right? But now I'm interested in representing phi of t in terms of x of t. Then what should I do? So I just want to eliminate this t factor. So I will replace t1 with t minus t. Okay. So then what will have phi of t minus t plus t. And on the right hand side I'll have x of t minus t. So this t and t will cancel. So I have phi of t is equal to x of t minus capital T. So by shifting x of t to the right by t capital T units, I got a new signal phi of t. And mathematically, how do I represent it? I just have x of small t minus that capital T, how much ever shift has happened, right? So this is for shifting to the right. So now you can guess what shifting to the left looks like. So I'll just summarize here. Shifting to the right by t seconds. Then what I have? Phi of t is equal to x of t minus t, right? So you can also observe that if capital T is equal to 0, then it is nothing but the same signal x of t itself. So next what we have? Shifting to the left by t seconds. So now what it will be? So it will just be x of t plus t, right? Because you can argue it two ways. You can either go ahead and derive like this, or you can say shifting to the right by minus t units is same as shifting to the left by t units. So you will just replace this minus sign with a plus sign. Okay, if this is clear, let's see some example. Let's say x of t is again the same, or we can take the same as triangular signal. So from minus 2 to 2, and let's say the amplitude is 2. This is x of t with respect to time. And I want x of t plus 2. How will I do it? What should I do? So I should just shift the signal to the left by 2 because it is plus 2, right? So if I shift it to the 2 by 2 to the left, then this minus 2 will become minus 4 and this 2 will become 0 and whatever was 0 will become minus 2, right? Then I will have this triangular waveform here. So this amplitude will still remain at 2, right? So you can also see this signal as advanced by 2 units or 2 seconds. So advance is nothing but left shift. And for delayed what you have? Let's go ahead and plot that also. So I have x of t minus 2. What will happen? So I just need to shift this by 2 units, right? So minus 2 will come to 0, 0 will go to 2 and 2 will go to 4. And I have this. This is 2 and this is 2. So this is delayed by 2 seconds. This is nothing but the right shift, right? So you can also find this mathematically, right? For example, if you want to find value of this waveform, let's call this phi 2 of t and this is phi 1 of t. I want to find the value of phi 2 of t at t equal to 2. So phi 2 of 2. So what will it be? You just need to substitute this here. So x of 2 minus 2 is nothing but x of 0, right? So whatever is here, whatever value is here, is nothing but whatever value is there at x of 0, which is nothing but 2. Similarly, x1 of, let's say I want to find the value of x1 of 0. Then what I have? X of 0 plus 2, right? So what is x of 0 plus 2? X of 2. So whatever value is at phi 1 of 0 is nothing but the value at x of 2, which is nothing but 0. So this is synonymous with our derivation as well. Okay, next we'll move on to time scaling. Okay, so we saw what is a time shifting. Now we'll see time scaling. For this case, again we'll consider some signal x of t. So let's say on one side it is t1 and on other side it is t2. Right? Or we can make this smaller, little smaller. Okay. And this is x of t. So scaling is nothing but we want to find some x of at. Correct? For a simpler case, let's say x of 2t. So what will be that signal? So you again have the time axis. So whatever happens at 2t here should happen at t in x of t, right? So whatever happens at t here should happen at t by 2 at x of t, right? So if here it is t1, then where will it be for x of 2t? It should be at t1 by 2, right? So I'll call it phi of t. Okay. So again here also the amplitude remains same, 1, and this side we have t2 by 2, right? So again you can see here, so phi of t1 by 2 is nothing but x of 2 into t1 by 2, which is nothing but x of t1, right? So here it is at t1 and x of t is going to 0 and phi of t is going to 0 at t1 by 2. And similarly for x of t2 by 2, if you see, again phi of t is going to 0 at t2 by 2. So x of t also should be going to 0 at x of t2, right? So t2 by 2 is nothing but x of t2. So you can see it just has shrunk. The signal has shrunk, right? But the origin hasn't changed. So origin is fixed, but the signal has shrunk. So there is also a nice analogy to remember this. So if x of t, if you imagine it to be an audio signal, and let's say you record it in a tape, and x of 2t is nothing but you're playing the audio signal in 2x. Similarly for even the YouTube videos we see, right? If you play the YouTube videos in 2x, it is nothing but equivalent to a time shrunk, right? Or time compression. So this is nothing but a time compression. So the signal is being played fast. Initially it is taking some, let's say t1 to t2, but here it is just t1 by 2 to t2 by 2, right? So here t1 can be negative or positive. It doesn't matter. But it matters if it is the origin, where is the origin present, right? So this should be minus t1. And if we say this is origin, then 0, 0, then now the t1 being positive or negative is mattering. Or in the normal case, if you see, if you just have any signal from t1 to t2, its time compression will just be t1 by 2 to t2 by 2. If this peak is occurring at some point t, then here it will occur at some point t by 2. So only the origin is not changing. And why it is not changing? Because some phi of t is equal to x of 2t, right? Then phi of 0 is nothing but x of 2 into 0, and 2 into 0 is nothing but x of 0 itself. So the origin is being fixed when you're scaling the time, right? This is just for your example, for your understanding. Yeah. So what is the other case? So if I have x of t is equal to, phi of t is equal to x of t by 2, then what will happen? So now it is just like expansion in time, right? so it will slow down. So here the signal is faster, right? Faster playback. If you want to slow down, what you do? You just take x of t by 2. So in that case, how will it look like? So this will go from 2t1 or minus 2t1 to 2t2, right? And the amplitude will be the same. So now you can see it has expanded. So you can call it time expansion, right? Time expansion. So in general, if you want to define some phi1 of t is equal to x of at. So a is always greater than 0. Here let's say a greater than 0. Then it is time compression. So the signal will shrink. And phi 2 of t is equal to x of at. If a is less than 0, then it is time expansion. Right? And the signal will expand. And in both these cases, origin remains unchanged. So let's consider some more examples. So let's say I have a rectangular pulse from 1 to minus 1 and x of t, and the amplitude is 1. Now I want, let's say, x of 2t, right? Then what will happen? It is just a compression. So the amplitude will remain same, and minus 1 will move to minus 1 by 2, which is 0.5, minus 0.5, and 1 will move to come into 0.5, right? And if I want, let me also shrink this, right, in space. This is shrinking in space, right? Now if I want x of t by 2, so it is nothing but expansion in time. So where will this be? So this will be larger pulse, longer pulse, right? And it will extend from minus 2 to 2. Okay. So next we'll see time reversal. Okay. And I think I made a mistake here. This is a greater than 1, right? So a greater than 1 and a less than 1. Sorry for that. Right? Because if it is greater, then it is results in compression, and if a is less than 1, it is expansion. So only coming to time reversal, we'll see the negative values now. So in simple terms, if we have x of t and t, let's say there is something here, minus t1 and t2. So phi of t is nothing but x of minus t. It is nothing but the reflection of x of t along the vertical axis. So whatever is on the right will go to the left, and whatever is on the left will go to right. So in other words, you can also imagine that you're just rotating this vertical axis 180 degrees. So then also the same operation results, right? If you're able to imagine. So what you will get? T, and here you will get this one. This will be minus T2, and this will be T1, right? And here again the amplitude, whatever is there, will remain same. And this is equivalent to recording an audio or video and playing it backwards, right? So whatever went in first will come at last. Correct? Again here if you see, the origin is unchanged. So whatever value it was having at 0, the same value it has here. But only thing is, like, it has reflected above the vertical axis, right? Reflection about the vertical axis. So whatever is there on the right will go to left, and whatever is there on the left will go to right. Okay. So now we'll see combined operations of all three. Combined operations of shifting, scaling, and reversal. So when they were individually, we were operating, what did we do? So whenever we made a reversal, we just replace t with minus t, right? So I'll write it down here. So for reversal, mathematically what we have done? Replaced t with minus t, right? And then before this what we had? Scaling. In scaling what we did? Whenever we compressed, we replaced t with some a times t, how much ever the compression ratio is, right? And for expansion, we replace t with t by a, and a is the expansion ratio. So for scaling, what did we do? Replaced t with at, correct? And a less than 1, greater than 1. So a less than 1 or a greater than 1. And in this, like, a is always greater than 0. Because if it goes to negative, then it becomes a reversal, right? Individually when we are speaking, when we don't want to mix them, we just say 0 less than a less than 1. And a can't be 0 because then it will just be a simple, it will just give x of 0, right? So that's something redundant, I feel. And so we'll consider a as greater than 0. And then what is remaining? Shifting, right? In shifting, what did we do? When we shifted to the left, we replaced t with t plus 2. And shifting to the right, we replaced t with t minus 2. So shifting replaced t with t plus or minus t based on right or left. So the plus 1 is left, minus 1 is right. Okay. So in general, a combined operation will look like something like this. So phi of t is x of at minus b. And a can be anything, right? A can be negative here. Negative. So if a is negative, then there is a reflection or reversal, right? Time reversal. So now you can achieve this phi of t in two ways. Okay, so let's see both ways. So first way. So first way, what I have x of t. Then what I do? I first time scale. Okay. So what will I get? I will replace t with t minus b. Right? So this is replace t with t minus b. So then what I do? I will, this is time shifting. Time shift. And then I will do the time scaling. Okay. So now replace t with at. So I will have x of at minus b. So let's say if a is positive, you just scale and leave it. If A is negative, we just need to do the time reversal. So let's make it mod here so that you're not confused. Correct? And what I do here, time shift by B, right? And time scaling by A, right? Or mod A. And then if A is negative, do the time reversal. Then you will get x of AT minus B. So this is first way. So let's take some example, right? To visualize this first way. So I will take x of t as something like this. So this is 2. Let's say this is minus 2, 0. And this is 2. This is t. And let's say I want to do x of 2t plus 3. Okay. So what do I first do? I time shift by b. So I should time shift by 3. So what will be the thing? So this is x of, let's say, t plus 3, right? So what will it be? Everything will be shifted left by 3 units. So 2 will go to minus 1. Minus 1. 0 will go to minus 3. And minus 2 will go to minus 5. Okay, I will have something like this. Amplitude will be 2. Now x of, then what should I do? I should time scale by a. Your a is 2. So now I should time scale by x of 2t plus 3. So here time shift by 3. Here now time scale by 2. So minus 1 will come to minus 1 by 2. Right? And minus 3 will be minus 3 by 2. Minus 5 will be minus 5 by 2. So the signal will look like this. Right? So this is x of 2t plus 3. Now you can also check. So I'll take some t as at minus 1 by 2, right? So it will be, I'll call it as phi of t. So I want phi of minus 1 by 2. So what will it be? X of 2 into minus 1 by 2 plus 3. So this is minus 1 plus 3 will be x of 2. Is that correct? So this point is synonymous with this point, which is correct, right? So you can cross check your answers this way also. Like you can pick any point and then try to substitute it here and then see if that same point corresponds to the first what we started with, the signal we started with. Okay. So this is the first thing. So now let's see the second way. Okay. So in the second way, what we have? Also, if you see here, we have only replaced t with at or t minus b, right? When this t minus b is there, we haven't multiplied the entire t minus b with a. For example, we haven't done a of t minus b, right? We haven't done it for time scaling by a. We just replaced t alone. So b is there and t alone we have replaced with at. Right? That is important to note. So then now you can see the second way easily. So in second way, so in the first way we did time shift by b first and then time scaling. So in the second way, it is opposite, right? So x of at plus b. So you have x of t. Okay. So first you do time. So you can do the time reversal if necessary. It's necessary. Right? Then you will have some x of t or x of minus t depending on whatever a is, right? Then you do time scaling. by mod A, right? So then what will you get? X of AT, correct? Then now we have to, for when you're doing time shifting, you have to replace T, right? Time shifting by B. So if you time shift by B, what you will get? A. Replacing T, it will be T minus B. Here it will be multiplication of with A, because you are replacing T, which itself is multiplied by A. But in the previous case, what you have? You have B already present and you are just replacing T with A, right? That difference you should know. So here what you will get? You will get AT minus AB. So you don't want AB, you just want B. So what you do? You just time shift by B by A. So then this will be B by A, correct? So then when you multiply, you will get AT minus B. So this is what we want. So you can combine these two steps, right? And you can just call it scaling, time scaling by A, right? Then here also you can do the same. So you can just combine these both steps and you can call it time scaling by A. So reversal is just like a special case of time scaling where you have the minus sign, right? Okay. So now let's try to work out the same example for the second way. So I will try to do it maybe side by side so that you can better understand, right? I will copy this, put it here. Okay. So in the second case, what do? I have the same x of t here. Okay. So it's first way and second way. So now I first scale. So time scale by A. A here is, so I need to find x of 2t plus 3. Okay, or I'll write it in another color. X of 2t plus 3. So time scale by 2. So if I time scale by 2, what will it be? So this will be 1, 0 and minus 1, right? Correct. Right, okay. So this will be x of 2t. So then what I have to do? I have to time shift by b by a, right? So b here is 3, b by a will be 3 by 2. So time shift by 3 by 2 plus 3 by 2. That means it is shifting to the left. So 1 minus 3 by 2 will be minus 1 by 2. So minus 1 by 2 and minus 1 minus 3 by 2 will be minus 5 by 2. So 0 will come at minus 3 by 2, right? So I have this signal. This is 2. So now you can see that these both are same signals. So even if you follow both ways, your final answer should be same. So if you made any mistake in between, then your one of the answers will be wrong. So usually what I would suggest is you can choose either way, but stick to one way, right? I feel like this is more easier because you don't have to take this factor of b by a, right? So considering that, actually you can go with the first method. You can stick on to that, and with practice, like you will actually like get used to it and you will not make any more mistakes. Initially, it is normal to make mistakes. So actually you do the shifting first and then do the scaling, right? Okay, next we'll see the classification of signals. So the first type is based on the independent variable. Okay. So in this case, we are considering time, right? So we can divide the signals into two. So one is the continuous time signals and discrete time signals. So by the name itself, you can see. So continuous time signals are continuous in values of t, right? Continuous time signals. They are continuous in time t. So for example, so this is one example. So at every value of t, the signal is defined. So x of t is defined at continuously it is defined at every value of t, or continuum value of t, we can say continuum. And the next one is discrete time signals. So they are defined, they have values only at discrete instance of time. For example, let's say 0, 1, 2, 3, minus 1, minus 2. So only at these places they have values, right? So specified only at discrete values of t. So since it is discrete, we can just represent as x of n, right? Where n is some natural numbers or like integers, right? 0, 1, 2, 3 and minus 1, minus 2, minus 3 and so on. So the in between, there is no value for the signal. It is not defined, right? So examples of these, if you see, for continuous time signals, you can take all the voltages, currents. So all naturally occurring things, right? It's continuous in time. Even our aging. Age is also continuous in time. As far as like quantum mechanics doesn't get involved and they say time itself is discretized, right? We don't go into that. And for discrete time, what do we have? Let's say the population. So population, usually they describe it as every year, right? They don't give at every instant of time. They describe it only at every year. They say it in 2022, 2021 and so on. So population, GDP, etc. Okay. So next is classification based on the amplitude. Classification based on amplitude or value of the signal. So again, they are divided into two types. So the first one is analog signals. So analog signals, they have continuous values. So they can take continuous values of amplitude. Right? Example, So this signal t, x of t, some signal. So you can see that the amplitude is varying continuously, right? And it can also be in discrete time. So if you just sample this signal, right, at instance, so we will have something like this, right? So again, here also, if you say the amplitude can take on any continuous values, then it is still an analog signal. So this is an analog continuous time signal, and this is an analog discrete time signal. So many of you may be confused with analog and continuous time and analog discrete time, right? Even analog can be in discrete time. Okay. So this can take values like 1.2, 1.4. Continuously it can take 1.21 also, right? So the second classification is digital signals. So digital signals, the amplitude can take only finite number of values. Okay. For binary, if you see, you have 0 and 1. So bi means 2. Similarly, you can have n-ary. So you can have some m values. M values you can have. Or it will be m minus 1 because 0 is included, right? So you can have m values. And for binary, m is equal to 2. So again, you can have a digital continuous time also. Digital continuous time. So you can see the signal itself is let's say I can take only values 1, 2, 3 or 0, right? Then you can see this time is continuous. So this change can happen at any instant. 1.1, 1.2, anywhere it can happen. You can see the time is continuous, but the amplitude itself is constrained to take only 1, 2, 3 or 0. So only 4 values, right? This is digital continuous time signal. What about digital discrete time? So we have digital discrete time signal. So here the x-axis or the time axis is discrete, and the amplitude is also discrete, 1, 2, 3. Okay. So now it can only take values like this. Here it is 0, 0, let's. So here it is 3, 2, 1, and here let's say it is 2, then 0, 0, 2, right? So you can classify these 4 based on the x and y axis, right? So the first one, analog and continuous, is both x and y can take continuous values. Analog discrete time is x-axis or the time axis is discrete, while the y-axis or the amplitude can be continuous. And in the third, if you see, digital continuous time, the amplitude is discretized, but the time can be continuous. And the fourth is digital discrete time signal. So here both the amplitude and the time axis is discretized, right? So next classification we'll see about periodic and aperiodic signals. So what is a periodic signal? So the signal should repeat itself after a certain interval of time. And it should happen continuously. So it should repeat in itself continuously. So if it repeats just once, then it is not sufficient, right? So if we have some x of t, then if we just shift it by x of t plus t naught, or shifted by t naught units, then let's say if it is repeating, if it is equal, then we can say that it is periodic. And this t naught is said to be the period. So this signal x of t is repeating every t naught, right? And this is for all t. So then the signal period is nothing but t naught. And the definition for period is the, so there is something called as the fundamental period. Fundamental period. So why fundamental period? Because if it is repeating for t naught, every 2 t naught, 3 t naught, or integer multiples of t naught also it is going to repeat. So the fundamental t naught period is the smallest t naught that satisfies this condition, satisfies the above condition. So for example, we'll just take, if we take a square wave, and let's say it is repeating. So 0, I said this is 1, and this is 2, so this will be 3, 4, and you will see another square wave. And here this side you will see -1, -2, and so on, right? So what is the period of this? So you can see this entire thing is being repeated, not just the square, even the empty spaces or where the signal 0 is being repeated. So here the t naught, the fundamental period is 2 units, right? So x of t. So x of t here is equal to x of t plus 2. And as you can see, for every periodic signal, because this equation is valid for every t, for all t, so the extent of the signal itself should be from -infinity to infinity. So the signal start from -infinity to infinity. So they have a huge range, starts from -infinity to infinity, and hence naturally their energy will be infinite, and we can calculate power, right? And another speciality about periodic signal is if we just know one period, right, then we can repeat them and form the entire signal. So it is just sufficient to know the information about one period of the signal. Right? To recreate the entire signal. So as an example, if we want to find the average over one period, right? Average over one period. So I can start from -t0/2 to t0/2 x of t dt, or I can start from 0 to t0 x of t dt. So I can start from anywhere, a to a plus t0 x of t by x of t dt. So anything, anywhere I start, if I have one full period information, then I can find the average. So it is equivalently, I can write it as T naught x of t dt, just as a subscript. So on the other hand, what we have is the aperiodic signal. So there is no special definition for aperiodic signal. It is just a signal which is not periodic. Which is not periodic. Okay. So next we have something called as a causal signal, and then non-causal signal and anti-causal signal. So if we have any signal x of t equal to 0 for t less than 0, then we call such signals as causal signals. So it is just a mathematical representation, and we actually assume that if the signal is starting from t greater than 0 or t equal to 0, then we say it is causal, alright? It's like saying we don't know what happened to the signal before t equal to 0. So we assume the value is actually 0. So from there we call it as a causal signal. And non-causal signal is nothing but when x of t is not equal to 0 for even for at any one instant, even if it's at any one instant. Right? So we'll write it as for any t less than 0, then it is called as a non-causal signal. Okay? And anti-causal signal is nothing but x of t is equal to 0 for t greater than 0, just the opposite of causal. So it is called as an anti-causal signal. So next we have the energy and power signals. So energy signal. So this is nothing but a signal having finite energy. Signal having finite energy. And we have a power signal. So power signal is signal having a finite and non-zero power. Non-zero power. So you can also say power signal as it has infinite energy. Right? But in practice, if you see, like, you cannot have infinite energy. So this is just for the mathematical definition's sake. For example, if you have a sinusoid, you can see it has an infinite energy and a finite power. So it is a power signal. But in reality, you cannot actually generate a everlasting sinusoid, right? Because it has an infinite energy and you have to give an infinite energy, which is not possible. But later in the course, we'll see how this mathematically helps us to formulate certain things, represent other signals in terms of this sinusoid. So there it is helpful. So we require these kinds of definitions to help us later on. And again, if you see, some certain signals can be neither be power nor energy signals. For example, if you have a ramp. So ramp is nothing but x of t equal to t. So it is just growing up with time, right? So even if it try to calculate the power, it will not converge, it will tend to infinity. So it is neither an energy signal nor a power signal. And if you see, if any signal is an energy signal, then its power will be zero. Hence, it cannot be a power signal. On the other hand, if any power signal, if you take, its energy is infinite. So, it cannot be a energy signal. So, one signal cannot be both energy and power at the same time. So, any signal can't be an energy and a power signal at the same time. So both can be both energy and power signal at the same time. So finally we have what is called as a deterministic and random signal. Deterministic and random signal. So a signal whose physical description is completely known, either in mathematical or graphical form, is called a deterministic signal. So on the other hand, which cannot be known, right? A signal whose values cannot be predicted precisely, but also, like, we can say something about the signal, like the mean value, average, or mean squared value, something. So but are known only in terms of probabilistic description, right? Probabilistic description, right? Such as average, mean squared, distribution, etc. is called a random signal. So we know one good example of a random signal, right? It is a noise. So deterministic signal, like all mathematically describable signals, are deterministic signal. Say for example, sinusoid, exponential, everything is deterministic. So we have come to the end of the video. I would suggest you to go back and read the book to get a better understanding. Have a great day.